So, hello everyone, this is the artificial chemistry session, and we have 3 speakers in this session. And first speaker is Enelo Orknam, and she's talking about modular combination of artificial chemistry. Please.
Okay, so this work somewhat follows on from previous work I've had in the last couple of years at Econ and ALIFE, but kind of moving in a bit of a different direction. Previously, we've been building artificial chemistries. Now we've kind of gone with actually building artificial chemistries is something we know how to do. We can build an artificial chemistry. What we don't know, what's really, really hard is getting them to do complex things on multiple levels. And what's really hard is then working out where those levels are and what we're doing. But we have lots and lots of these systems, and I think most of them are on different levels to each other. There's very few of them that are actually, I would say, on parity with where they're aiming at. So maybe if actually we could make use of that existing resource, or we could get there a bit quicker in terms of these bigger, more multi-layered, complex system. So this is basically the beginnings of a framework towards being able to combine existing artificial chemistries. So one of the problems we have with artificial chemistries in these different levels is the many different attributes of an artificial chemistry that vary so hugely between different systems. So some of these systems are completely aspatial. Some of them are entirely spatial. We've got things with kinetics, elasticity, physical linking, dimensionality. We've got things that have none of those properties. We can't even determine whether we should have events or not, or whether we have implicit or explicit rules. Some of ours don't. Some systems have dynamic states, some systems don't. And all of this means that these... You can even see this in different representations of actual chemistry, and how actual chemists think about chemistry on different levels. You get down to physical chemistry, and everyone starts going, actually, you know that stick and ball diagram you've been taught about since you were very small? Complete rubbish. But you talk to chemists higher up in organic chemistry and all that, and that model perfectly fine. Fine, no problems there. And this makes it very hard to do comparisons. It makes it very hard to get these systems to work together, and it makes it very hard to understand where they sit relative to each other. So what we'd like to propose is this idea of modularization of our chemistries. So strip back and contain these attributes a bit more, so we can see where they are in a chemistry. We can see what they're doing. And this is a very simplified version of our system that I'm using for today's presentation, but it covers everything we need for this level of talk. So today I'm modularizing with actions. So this is in your system if something bumps into something else, if something links with something else, if it's something that's destroyed, any sort of interaction happening between your particles. We've got an observer, and this to me is one of the most important objects in these systems, because it's really important that we define what we're looking at, and when we're looking at it, and when we're not. Because we sit here and we say we have complete information about these systems, but actually we don't. We don't actually record the exact run on the exact computer and the exact interactions happening in these CPUs in the majority of cases. So we don't actually have absolute complete information. What we have is what we observed. We have what we output from our system. And it's important to acknowledge that because as systems get more complicated, and particularly as we want our systems to interact with each other, we need to know what they can see and how they see it. And then we've got these last 3 bits. These are tanks. So I use the term tanks just generic. It's a container. But then so is our environment. Our environment is a container. But our environment, these just store values. So in an artificial chemistry system, generally speaking, we have values we're interested in, that we think of as our objects, that we think of as our active objects, and things that we don't. Much like natural chemistry, you put a couple of chemicals in a beaker, stir it around, and you spend forever analysing that reaction. Well, everything in that beaker is also in that beaker, and that beaker is also made out of atoms and molecules. So let's not get too heavy-handed with saying that the beaker is different from the chemicals in it. But it is in terms of what we want to do with it. So we call what's in the beaker particles, and we call everything that isn't those the environment. That's how we've called it in this system. You can give it a different name, but in general, in artificial chemistry systems, we decide that there is one subset of values or objects or things in our system that are our active objects, that are our particles, that are the things we are interested in.